Let me give another economic illustration of differentials in general, not necessarily the total differential, but differentials in general. And this is the concept of the elasticity of one variable with respect to another variable. Suppose we just begin with this simple case. Suppose y is a function of x. Y is a function of a single variable. Then you can talk about the elasticity. Let me use a capital E to denote elasticity. The elasticity of variable y with respect to variable x, y comma x, is just this. It is the proportional change in y, which is just dy over y. See, dy is the change in y. If you divide it by y, then this becomes the proportional or percentage change in y, divided by the proportional change in x. So the elasticity of variable y with respect to x is just the percentage change in y divided by the percentage change in x. Okay. Now, a more compact way to write this is this. dy dx, which is the derivative of y with respect to x, times x over y. And now this expression, dy dx times x over y, simply gives you the elasticity of y with respect to x. Now, you are most familiar with this in talking about the price elasticity of demand. If we're talking about the price elasticity of demand, usually we use the symbols Q and P. So let me rewrite this in an economic context. Suppose we have quantity demanded is a function, and I'll use f of p. Quantity demanded is a function of price. Then the elasticity of Q with respect to P is just dQ dP times P over Q. And what this price elasticity of demand measures is the percentage change in quantity per percentage change in price. For example, suppose the price elasticity of demand is -1. What does that mean? At a certain point on the demand curve, a certain value of P and a certain value of Q that corresponds to that value of P, the price elasticity of demand at that point is -1. Then in words, what does that mean? Yes, John?
1% change in price causes quantity demanded to fall by
Okay. Okay. Let me just rephrase it just a tiny bit. If the price were to rise by 1%, quantity demanded would fall by 1%. Or if the price were to fall by 1%, what would happen to quantity demanded? It go up by 1%. So they move in the opposite direction, a 1-to-1 ratio. Okay. Probably it's easiest to think of a price increase. So if price rises by 1%, quantity demanded will fall by 1%. Okay. Okay. If the price elasticity demand were 1.5, what would that mean? Brittany, what would that mean if the price elasticity demand were minus 1.5?
That if the price increased by 1, or if the price percent increased by 1, then it would find.
Exactly. If the price increased by 1%, quantity demanded would fall by 1.5%. Okay. If the price elasticity demand were -2, that would simply mean if the price rises by 1%, quantity demand falls by 2%. So the larger this value is, an absolute value, then the more sensitive quantity demand it is to changes in price. Okay. For example, if I give you some real world examples, the price elasticity demand for cigarettes has been estimated to be approximately -0.4. -0.4. So that means if the price of cigarettes were to rise by 1%, quantity demanded would fall by only 0.4%. Or to put it in another way, suppose the price rose by 10%. Quantity demand would fall by how much? 4%. Just move the decimal over 1. Yeah. Okay. Okay. The lower that value is, an absolute value, the less sensitive demand is to price changes. Okay. Let me give you a mathematical example. Suppose we have a linear demand curve. Quantity demanded is equal to 100 minus P. If we were to graph this demand curve, it would look like this. Now let me graph it with Q on the vertical axis and P on the horizontal axis. So it would look like this. Vertical intercept is 100. Has a slope of -1. So the demand curve looks like this. It would cross the horizontal axis at 100. If the price were 100, quantity demanded would be 0. So our demand curve looks like that. Now, our expression for the price elasticity demand, let me leave out the D subscript, okay? It's just this. Again, it's dQdP times P over Q. Now, in this particular case, what is dQdP? In this particular case, dQdP is always what? -1. If you take the derivative of Q with respect to P right here, it's just -1. So dQdP is always just -1. So we substitute that in for dQdP. So the price elasticity is just -1 times P over Q, or it's just minus P over Q. The price elasticity is going to vary at every point. For example, if you take the midpoint, suppose the price is 50. Plug into that demand curve, quantity demanded is 50. At this point, what is the elasticity? Just -1, because it's -50 over 50 is -1. But notice, this price elasticity demand is going to vary from point to point because the ratio P over Q varies from point to point. For example, if P is equal to 80, then Q is 20. And what is the elasticity demand at this point? Anybody? David? What would the elasticity of demand be at this point? No? David, what's our formula for the price elasticity demand?
Are you asking for like the formula, just the generalized formula?
Yeah, the generalized formula is what? Oh, okay. Is this not clear? Minus P over Q.
Yeah.
So that's the formula for this particular demand function. The elasticity is just minus P over Q. So P is equal to 80. Q is equal to 20. So the price elasticity demand at this point must be 4, just -4. So this illustrates that the price elasticity demand varies from point to point along a linear demand curve. It's not constant. As you go down the demand curve, the elasticity is, in absolute value, is going to rise because your ratio of P over Q is getting bigger and bigger and bigger. Okay. At the midpoint, the price elasticity demand will always be -1. Okay. So this does mean you have to be careful. Okay. The price elasticity demand, Bernard, is minus P over Q. So P, we assume P was 80. Q is equal to 20. So it's just a minus 80 over 20 or -4. Okay. So the price elasticity demand is really a point measure, and it can vary from point to point along the demand curve. Okay.